Welcome to our first lecture in inorganic chemistry. We're going to talk about atomic structure, and the first part of that is to talk about quantum mechanics. This is from chapter 2 in our textbook. We'll start with the Bohr model of the atom and then see how quantum mechanics has changed that picture of the atom, and give an example of the particle in a box. In later lectures, we will continue chapter 2. So the Bohr model of the atom was actually developed in 1913 by Niels Bohr, where he applied the new idea of quantized energy for an atom to the orbit using classical mechanics to develop the orbit model of the atom. And so we kind of fused the two, and we talk about orbits of electrons around the nucleus. And here's a simple model of a hydrogen atom, and using classical Coulombic attractions and stuff, Bohr proceeded then to solve the energy problem that had been observed looking at atomic spectra. And this actually is an excerpt from my version of his derivation, which can be found on my website. And for this work, he received the Nobel Prize in 1922. And the another main concept that came out of this Bohr model is the principal quantum number n, and n determines the energy of the orbit, or the energy of the electron as it orbits the nucleus. The energy equals negative some constant times z squared, where z is the atomic number for a hydrogen-like atom, and then n is the principal quantum number squared, where this k is equal to 13.6 electron volts, which is the Rydberg constant that had been determined from spectroscopy. Well, while this was a big breakthrough in understanding atoms and explaining the spectra, this picture of the atom quickly became obsolete with the continuing development of the quantum mechanical theory, in particular wave-particle duality. So ever since the 19th century, light was understood as a wave, and Maxwell's equations explain the electromagnetic forces and properties of light. And then J.J. Thomson, right at the end of the 19th century, actually discovered the particle of an electron, and was able to quantify it, weigh it, and determine its charge. However, then after the turn of the last century, Planck described the energy of light in terms of packets he called photons. And so this gives a particle picture of light. And so to kind of complete our understanding of nature, when we look at electrons, it turned out in an experiment in 1924 by de Broglie that electrons can behave as waves. So if electrons behave as waves, then this discrete orbit picture of an electron around an atomic nucleus can't be accurate. And so we're going to have to change our picture of the atom to help us along that way. Here's another development from quantum mechanics, which is the Schrödinger equation. Yes, that's the same Schrödinger from the Schrödinger cat thought experiment. And the basic Schrödinger equation is that you have a Hamiltonian operator working on a wave function, psi, that determines the eigenvalue or energy level of that wave function. The time-independent three-dimensional version of that looks like this here, this Hamiltonian operator, which is a partial derivative in x, y, and z, working on the wave function will give the eigenvalue for that wave function. And this is a general formula that can be applied to any particle, but the quantum mechanical effects become apparent at extremely tiny sizes and masses, such as for an electron. Well, that's partial derivatives, which is a lot of work, which hopefully you've already done in your physical chemistry class. And so let's just look at the simplest system, which is the situation when you have a particle in a box. And the idea of the particle in a box is that you have a charged particle that is confined in a one-dimensional space, let's say the x-axis here, and it's confined between 0 and some one fraction, the whole unit here of this x-axis. And it's confined by extremely high energy, say electrostatic potential energy, at the edges of this box. So the particle is in here, and in a classical view, we'll say, well, here's the particle with my red dot here, and if it's at 0 energy, well, it's just lying here somewhere in the box. If we add a little energy, well, it starts to move around. Energy is in the x-axis here, so it can kind of move around. And here we go. We're going to play Pong here off the walls of the box. Well, quantum mechanics has a different view and says that the electron, the small charged particle, behaves as a wave, and solving the Schrödinger equation gives us the curve of that wave. And so at the end here, at 0 with the high potential, it can't be there, so it's going to be at 0 energy, the wave, and it'll also be 0 energy here. That's the boundary conditions. And then we're going to connect that with a nice curve. Okay, well, my drawings aren't that great. But anyway, so that would be actually the ground state of this particle as it behaves as a wave in this electrostatic potential box. And then if we add energy to it, energy is quantized, the particle jumps from the ground state to the excited state, and the curve gets sharper, and then has that shape. And we'll actually look at some of these formulas in your textbook and also in our worksheet for a class period. One other thing to point out about this wave function is that now at this higher energy we have a point where the curve crosses the x-axis, and so it has 0 potential here. I'm drawing now the shape of the wave function. Okay, and so this is called a node. So we can see that as we increase the energy, we add nodes to the wave. So the main points to look at right now, we'll explore that more when we meet together and also in our next lecture. So thank you for your attention, and we'll see you next time.